In the last MEB video, we performed our very first example problem for an open system energy balance. And in the process of calculating how much heat we would have to add to the process unit, the problem statement was very forthcoming, and it gave us a value for delta H hat. However, most textbook problems will not give you a value for delta H hat, and certainly not in the real world will you ever be given what delta H is. So therefore, this video will cover what you should do if you're not given delta H and how you can calculate it. And we'll talk much more about this when we get to chapter 8 stuff, but we'll start off with 3 of the tables that are in the back of the book that we have not discussed yet. These are tables B5, B6, and B7. They're called the steam tables, and they describe the internal energy and the enthalpy for water in its various states. So anytime you have a problem involving water, the steam tables are going to be essential for solving energy balance problems related to that. So I'm going to go to the textbook, and instead of writing out notes like I usually do, I just want to highlight some things in the textbook, and then I'll show you where the steam tables are and how you can read them. This is section B5 of your textbook. The very first thing that it mentions is that, remember, you cannot measure the absolute value of internal energy or enthalpy, similarly to how you cannot measure the absolute value of a potential energy, because it must be measured relative to a reference state that you arbitrarily assign as having 0 energy. And like I said, internal energy and enthalpy are no different. In order to calculate what they are, you have to reference some state. So many tables or many sources that you can go to will arbitrarily set this reference state to be 0 C and 1 atmosphere. You could also set it to be 32 C or 100 C or whatever else you want. But 0 C and 1 atmosphere are commonly chosen because 0 is the freezing point of water and 1 atmosphere is regular atmospheric pressure. So you should keep in mind that anytime you see tabulated values for H or U, these are going to be relative to this reference state, this arbitrary reference state. You may also see negative values for delta H and delta U. And keep in mind that, again, you can't have a negative energy. It's just negative when reference. It just means that that value is lower than your reference state, which is allowable. So I encourage you to read the rest of 7.5. And we're talking about the steam tables in this video. So in the steam tables, you'll oftentimes want to look in the footnotes just to check and make sure what the reference state is. But if you're using the same table for multiple data collections, then it's permissible to assume that the table uses the same reference state. I mention this because you want to be aware of, if you ever have to use separate tables for different purposes, you want to make sure that they use the same reference state, because that's the only way that you can compare. So once again, if you use the same table, you don't have to worry about the reference state. If you use different tables, you should check to make sure that the reference state is the same. So once again, I recommend reading the rest of section 7.5. This explains in much more detail what a reference state is, if what I just said was confusing. This is also the first time that the book refers to H and U as state properties. And this means that it only depends on the current thermodynamic state of the system. It does not depend on the path. And this will become much more important later on when we talk about not water and trying to calculate delta H and delta U. All right, so let's go back down to the steam tables. There's a section on the steam table as well that I recommend that you read in more detail, but I will just skip straight to the steam table and show you how to use it. So here we are on table B5, and B5 is titled Properties of Saturated Steam, the temperature table. So the first thing to note is that table B5 is for saturated steam. Now, what does that mean? A few videos ago, I drew the following phase diagram for water. And I noted that water's phase diagram looks like this. Remember, the solid-liquid equilibrium line is slanting to the left, which is unusual. And remember the phases of matter for the water phase diagram. I have solid, liquid, and vapor. So when I say saturated steam, this is water that is on the vapor-liquid equilibrium line. So again, saturated steam refers to all of these. So because I am saturated with one component, Gibbs phase rule gives me 2 plus 1 minus 2. So 2 is the regular Gibbs phase rule number for the out front, plus one component for water, minus 2 components because I have 2 phases because I'm saturated and at equilibrium. So steam is, once again, at the equilibrium for vapors and liquids. And 2 plus 1 minus 2 is equal to 1, which is 1 degree of freedom, meaning that in order to calculate what the energy or enthalpy for steam is, I need to specify one variable. In table B5, the variable that is specified is temperature. In table B6, which I'll talk about in a moment, the specified variable is pressure. So table B5 and B6 have exactly the same data on it. The only difference is what the specified variable is. So keep that in mind. The leftmost column on this diagram is the temperature in degrees C. So as I said, temperature is specified here, so it goes just in 2-degree increments for a while. I think it's 2-degree increments all the way. And notice that in the footnotes, it does not say what the reference state for this table is. However, if I look at the values of the table, I find that the internal energy and the enthalpy for water is 0 at 0.01 C and 0.00611 bar. So I mentioned just a couple of seconds ago that the reference state is commonly assumed to be 0 C and 1 atmosphere, but that is not the case for this table. This table looks like it uses the triple point of water. That's what this temperature and pressure refers to. So once again, that's just something to keep in mind. It should not affect what your final answers are because the amount of energy that you need when you're doing calculations is independent of your reference state, but you will need to be aware of this when you're solving problems. Let's just keep going column by column. The P in bar is the pressure that corresponds to this temperature. So once again, for vapor-liquid equilibrium, where I have 2 phases, which is what saturated steam refers to, if I set what the temperature is, that is, if I set values of temperature along this axis, then there's only one corresponding value of pressure that corresponds to that temperature. And this is what's being reported here in this column. So this is the saturation pressure corresponding to this temperature. The next 2 columns are the specific volume. So this is the inverse of density for water and steam. So we have been using 1,000 kilograms per meter cubed for water as the density. So therefore the inverse, the specific volume of water, would be 0.001 based on that. And if you look at how the specific volume of water changes as you go down and increase temperature, notice that it doesn't really change all that much. You have to get out to the 6th significant digit or the 5th significant digit before it starts to matter. So for this reason, this is why we commonly just assume that the specific gravity of water, or the specific volume, I'm sorry, is 0.001, corresponding to the density equaling 1,000. Now steam is water, but it's in the vapor phase, not the liquid phase. And therefore the specific volume would depend on the ideal gas law. However, for steam, you should always, so I mentioned that we're always going to be assuming ideal gas in this class, but this is an override to this rule. If you have thermodynamic data, and in this case you do, this takes precedence over the ideal gas law. So for example, if I had the pressure and the temperature of steam and it was very low, right? It's possible that the ideal gas law might work and this would actually be the molar volume. So you'd have to do the ideal gas law where you take the number of moles over to the other side, and you would have to calculate what V under bar is. It's RT divided by P. And because you have R and T, you could calculate what the molar volume is. And then you'd have to convert this molar volume into a specific volume. So you'd have to multiply or divide by the molecular weight of water, and you might get this answer, right? But you might not. And that corresponds to the fact that the ideal gas law is not very accurate for a range of pressures and temperatures. So therefore, if you ever have to calculate what the density or what the specific volume of steam is in its vapor state, instead of using the ideal gas law, you should always use the steam tables, because in general, tabulated data is always going to be your most accurate bet instead of an equation. Okay, so that's the first 2 columns after you get past the temperature and pressure columns. The next 2 columns refer to the internal energy, U hat, in units of kilojoules per kilogram. And once again, it's relative to liquid water at the triple point, and all these numbers are the kilojoules per kilogram relative to that reference state. Remember again that they are not absolute values. Notice here that the internal energy for steam is much greater than the internal energy for water, and that's to be expected because in general, vapors are at a higher energy state than liquids, and that should make sense thinking back to your chemistry courses. The next three columns are enthalpy, specific enthalpy in kilojoules per kilogram again, where you should notice that the internal energy is equal to the enthalpy for water, for liquid water, for a wide range of conditions. And we'll talk about that in more detail later on when we talk about things that are not just water. Here, once again, the enthalpy for steam in its vapor form is much greater than that for water. And this middle column is the enthalpy of vaporization. So this is merely the difference between water in its vapor state and water in its liquid state. Notice that the enthalpy of vaporization is changing as a function of temperature. And remember, we've seen enthalpy of vaporization before in the Clausius-Clapeyron equation. So another way to write this is delta H hat sub V, or sub vaporization. And this is something you could look up for water, but again, this is going to be relative to some state at some temperature and pressure. So again, it's going to change as temperature changes, and therefore, if you had a large temperature interval and you wanted to use the Clausius-Clapeyron equation, you could not assume that the enthalpy of vaporization is going to be constant. All right, so I'm kind of jumping around a bit and bringing terms back that we've heard before, and this is why that Chapter 6 stuff was necessary introduction for Chapter 7 stuff. Okay, the second page of Table B5 is more of the same. The only difference is that you have higher temperatures, so it keeps going all the way up to 102 C. I'll say that Table B5 and B6, we'll talk about that at the end, but I mentioned that B5 and B6 have the same information technically. It's just switching what variable is specified. B5 has much less information, however, so keep that in mind as well. All right, let's move on then to B6. This is properties of saturated steam, the pressure table. So once again, we have saturated steam, meaning we have to set one variable. And in this case, the variable that is set is the pressure. After you set the pressure, you can then know what the temperature is by using the fact that if I constrain vapor-liquid equilibrium to occur and I set one variable, I can read the other variable off the graph. Okay, so B6 once again has the same exact information. So let's just take, let's pick a number that I'm confident is there. So let's do, let's look for comparison purposes at 24 degrees C and 0.03 bar. So let's look at the internal energy for water. Liquid water at that state is 101. So let's go back up to table B5 and find where temperature is 24. And remember, on my other table, I had 0.03 here. So I'm not exactly at the same temperature, but it's very close. And 100.6 is very close to my other value. So once again, it's the same values, just different set points and different intermediate values that you can get from the two tables. Other than that, same exact information. Now let's move on to table B7. B6 is much more extensive, by the way. It covers a wider range of pressures and temperatures. So you have to scroll down multiple pages till you get to table B7. Now B7 is the properties of superheated steam, and it doesn't say this, but it's also of subcooled liquid as well. So on my phase diagram for water, I'll just draw a quick little cartoon in the upper corner. Superheated vapor corresponds to this entire region, and subcooled liquid corresponds to this entire region. So it's not the entirety of the regions, but we're just talking about places on the phase diagram that are not on the equilibrium curve anymore. So by Gibbs phase rule again, I have 2 plus 1 minus 1. So one component for water, one component meaning liquid or vapor, but not both coexisting together. That equals 2 degrees of freedom. So because of that, I have to specify both pressure and temperature to be able to calculate what the variables are. So pressure is on the y-axis and temperature is going to be on the x-axis. And the table goes down like this. Now it has values for saturated water and saturated steam as well. So it does have the same information again as B5 and B6. However, the points are spaced further apart. So for instance, on the pressure table, I have many more data points in between 0.1 bar and 0.5 bar that are missing from this table for the purposes of making it smaller and not so overwhelming. I mean, it is overwhelming, but you can imagine if it included all the data points, it would just be an enormous table. So that's these two columns, the difference between saturated water and saturated steam. Now over here is I have the two-dimensional space that I can go to look up the enthalpy, internal energy, or specific volume. So say for instance that I had steam at 20 bar and 75 C. I would go to 20 bar, then scroll over until I get to 75 C, and this would give me the values for, this would be liquid water at this state. That's what this weird stepping thing refers to, by the way, as well. This is the saturation point. So below this, in this staircase region here, under, this is the liquid water region, above is the superheated vapor region. And you can note that by noticing that the enthalpy and internal energy are both much less for the liquid than it is for the vapor. And the difference is, once again, the enthalpy of vaporization. Okay, let's continue to note things. I just want to make a couple more quick points about this table. Notice that for liquid water, as the pressure increases, so the pressure increases in this table pretty fast. It goes from 1 to 5 to 10 bar, which are the same thing as atmospheres. Yet the internal energy and enthalpy of water is not going to change very much. So just changing the pressure from 1 bar to 20 bar only makes it a change from 209 to 211. So that's not that much. In contrast, look at the change if I'm at 0.5 bar of going from 50 C to 75 C. It goes from 209.3 all the way up to 313.9. So from this, I can glean that temperature is much more of a factor on internal energy and enthalpy than pressure is. Right, specific volume is not going to change much for liquid water, but it will change a lot for superheated steam. All right, beyond this point, I don't have any more data points for saturated water and saturated steam. Think to yourself about why that is. And the answer is because it's beyond the critical point. So in this region, I'm supercritical steam. And therefore, I don't have any vapor-liquid equilibrium occurring anymore, which is why this liquid water region ends as well. So data points out here are somewhere in between liquid and vapor, but not both. All right, this table is also 2 pages, so you have some more data points, some more temperatures out here. One more thing I'll note is that because you don't have a lot of data points, say that you wanted the properties of superheated steam at 1 bar and 230 C, for example, well, then you're in between 200 and 250. So in order to do this type of problem and look up what this value is, you'd have to interpolate. And this, I showed you how to interpolate in a previous video, so you may want to revisit that video or look up on the internet how to perform an interpolation should you need to do it. That will conclude this video about the steam tables. By doing example problems in the future, I hope to get you a lot more familiar with the steam tables, but this required a whole video's worth of introduction. So hope you enjoyed watching. I'll see you in the next video.